Let's solve a second set of problems where we'll be required to find entropy values in tables. Using the appropriate tables, determine the change in specific entropy between the specified states in BTUs per pound mass R. Show the states on a sketch of the TS diagram. And then we're given 4 particular problems. Let's begin with the first one. We have water at a pressure of 10 psi, and it's a saturated vapor. So state 1 is fully defined. State 2 has a pressure of 500 psi and a temperature of 700 degrees Fahrenheit, so it is also fully defined. Let's see what we can find out about state 1. We'll go to the water saturation table at 10 psi, and we're given that we have a saturated vapor. So the specific entropy of state 1 is just S sub G, and the table value for that is 1.7877 BTUs per pound mass R. Now state 2 will start out in the saturation table at 500 psi, and we'll see that the saturation temperature at 500 psi is 193 degrees Fahrenheit. But our temperature is greater than that. The temperature of this state is 700 degrees Fahrenheit. So that tells us that state 2 is a superheated vapor. So then we can go to the superheat tables at 500 psi and 700 degrees Fahrenheit, and we get a value of specific entropy for state 2 is 1.6112 BTUs per pound mass R. And now we can calculate delta S, which is what we were asked to find. Well, delta S is just S2 minus S1. And we have those values from the table, and we can subtract them. And we get delta S is minus 0.1765 BTUs per pound mass R. And if we plot this on a TS diagram, this is what we will see. State 1 is a saturated vapor at 10 psi. State 2 is a superheated vapor at 500 psi and 700 degrees Fahrenheit. And notice that with this negative sign, we notice that the value of entropy at state 2 is less than it is at state 1. And that shows up on this diagram. This way we can see that the entropy at state 2 is a smaller value than it is at state 1. Our second problem is with ammonia at a pressure of 140 psi and a temperature of 160 degrees Fahrenheit. That defines state 1. And at the second state, we have 2 independent properties defining it. We have a temperature of minus 10 degrees Fahrenheit and an enthalpy of 590 BTUs per pound mass. So let's see what we can find out about state 1. We'll go to the ammonia saturation table at 140 psi, and we see that the saturation temperature is 74.75 degrees Fahrenheit. But this temperature at 160 is higher than the saturation temperature. So that tells us that we have a superheated vapor. So then I'll go to the ammonia superheat table at 140 psi and 160 degrees Fahrenheit, and I'll get the value for specific entropy at state 1 is S1 equals 1.3025 BTUs per pound mass R. Now for state 2, again, I'll start in the saturation table. T2 is minus 10 degrees Fahrenheit, and we'll note that the value of enthalpy that we're given, this 590, is in between H sub F and H sub G. So that tells us that this state is a saturated mixture. So I'm going to grab values for H sub F and H sub G and S sub F and S sub G. And the first thing we'll do is calculate the quality at state 2. It's just the enthalpy at state 2 minus H sub F over H sub G minus H sub F. We have these values from the table. We get the quality at state 2 is 0.9688. So now we can calculate the entropy at state 2. It's just S sub F plus the quality times S sub G minus S sub F. And so we can plug in those values that we got from the table. And we calculate that S2 is 1.2144 BTUs per pound mass R. Now we can calculate the change in entropy. So delta S is just S2 minus S1. We'll plug in the values we calculated. And we get delta S is 0.012 BTUs per pound mass R. And let's plot that on a TS diagram. State 1 is a superheated vapor at 140 psi and 160 degrees Fahrenheit. State 2 is a saturated mixture, which has a quality of 0.9688, and it's at minus 10 degrees Fahrenheit. And the saturation pressure at minus 10 degrees Fahrenheit, the table tells us the saturation pressure is 23.74 psi. We can also see that from delta S being positive, that S2 is greater than S1. Let's look at the third part of this problem. We have air as an ideal gas at a temperature of 80 degrees Fahrenheit and a pressure of 1 atmosphere. Those two independent properties define state 1. State 2 is at 340 degrees Fahrenheit and is a pressure of 5 atmosphere. So we need to know temperatures in absolute degrees. So since we're given Fahrenheit degrees, we'll add 460 to each one, and we know that T1 is then 540 degrees R, and that T2 is 800 degrees R. So let's calculate delta S for an ideal gas using the air tables. What you'll notice in the air tables is there's not a value of S, but there is S with this little degree sign. I call it S naught. There might be other names for it. And with that value and the gas constant and the pressure, we can calculate delta S. And this is the equation that we use. Delta S is S naught at temperature T2 minus S naught at temperature T1. That quantity minus the gas constant times the natural log of P2 over P1. So let's see how this works. First, let's calculate a gas constant for air. So the gas constant for air is the universal gas constant in English units, which is 1545. We'll divide that by the molecular weight of air, which is 28.97. And that quotient will have units of foot-pounds force per pound mass R. I would like to get that into BTUs, and there's 778 foot-pounds force is equivalent to 1 BTU. So I calculate the gas constant for air is 0.06855 BTUs per pound mass R. So now let's go to the air tables. We'll look up two values in the air tables, so one at T2 and one at T1. So the value of S naught at 800 degrees R from the table is 0.69558, and the value of S naught at 540 degrees in the table is 0.60078. So delta S is just S naught at T2, which is 0.69558, minus S naught at T1, which is 0.60078, then minus the gas constant R, which is 0.06855 BTUs per pound mass R, times the natural log of P2 over P1. Both were given in atmospheres. We calculate that delta S is negative 0.0155 BTUs per pound mass R. Let's plot that. We have a temperature entropy diagram. State 1 is a temperature of 540 degrees R and a pressure of 1 atmosphere. So I'll plot that here. And it has a specific entropy of S1. Now state 2 is at a temperature of 800 degrees R, a pressure of 5 atmosphere, and we notice that S2 is less than S1 because delta S is negative. Let's look at our final problem. Oxygen is an ideal gas. The temperature is constant for this process. T1 is equal to T2, and both are at 500 degrees R. The pressure of state 1 is 10 atmospheres. The pressure at state 2 is 5 atmospheres. Well, we're going to use this same equation that we used in the previous problem, where the change in entropy for a process is S naught at T2 minus S naught at T1 minus R times the natural log of P2 over P1. We can plot this already on a TS diagram. It takes place at a constant temperature, and so it's a horizontal line on this TS diagram. And state 1's at 10 atmospheres, and state 2 is at a lower pressure of 5 atmospheres. Let's calculate the gas constant for oxygen. It's the universal constant, 1545, divided by the molecular weight of oxygen, which is 32. And that having a value or units of foot-pounds forced per pound mass R, I'm going to convert that to BTUs. And I have the gas constant for oxygen is 0.06206 BTUs per pound mass R. Now, T1 is equal to T2, so S naught of T2 minus S naught of T1 it's going to equal 0 because S naught for the same temperature is the same value. So the first term in my equation, where we have delta S is S naught of T2 minus S naught of T1, that's going to be 0. And then we subtract from that the gas constant times the natural log of the pressure ratio. So we subtract the gas constant times the natural log of P2 is 5 atmospheres over P1, which is 10 atmospheres. And I get delta S is 0.04302 BTUs per pound mass R.